mean when we say reaction? We are basically referring to chemical change. You must remember from your previous grades that in science we have got two types of change. One is physical change, where the object is basically changing state, maybe from solid to liquid, from liquid to gas, but the chemical formula is not changing. We refer to such as physical change. But in chemical change, you have got reactants that are chemically combining in a fixed ratio in order to give you products with a different chemical formula. Just for example, I gave you magnesium solid plus 2HCl arc to give us magnesium chloride MgCl2 arc plus hydrogen H2 gas. Now, I also gave a molar ratio down there, which is 1:2:1:1, meaning to say 1 mole of magnesium is reacting with 2 moles of hydrochloric acid to give us 1 mole of magnesium chloride and 1 mole of H2 hydrogen gas. Now, what is the rate of reaction? The rate of reaction can be defined in two ways. One, it is the amount of products produced per unit time. So we can measure the rate of a chemical reaction by means of measuring how much of the products is being produced per unit time. Mathematically speaking, we can say the rate of reaction is equal to amount of product divided by the time. So it can be the amount of products in mole divided by the time in seconds. Like in the example that I gave you above, we can measure the amount of the products or one of the products, and then that will give us an indication of the rate of reaction if we divide it by the time. So we can measure the amount of hydrogen produced with time because it is a gas. So as soon as it is produced, it's going to escape from your reaction mixture, and then we can measure it by means of a measuring syringe, and then we determine how much of it is being produced per unit time. That will give us the rate of reaction. Another way we can also determine the rate of reaction is the amount of reactants used up per unit time. In other words, we are saying we can get the rate of reaction from this mathematical equation. Rate of reaction is equals to amount of reactant used divided by time in seconds. So these are the two ways by which you can define and determine the rate of reaction, right? Amount of products produced per unit time, or the amount of reactants used up per unit time. Because you must remember, as your reaction progresses, the amount of reactants will be decreasing because they are being used up to produce products. And what do you expect to happen with the products? The amount of products will be increasing with time. Now, these reactant particles, how do they react? They react according to the collision theory. What does the collision theory say? It says the reactant particles must collide with sufficient energy and correct orientation for a reaction to occur. So this chemical change that we are talking about does not just occur anyhow. It only occurs if the two conditions are met, that the particles are having sufficient energy and they are in the correct orientation. And the minimum amount of energy required for a chemical reaction to occur is called the activation energy. So now let's proceed further to describe the various factors that affect the rate of reaction using the collision theory. Let's start by looking at temperature, right? Let's look at temperature. What is temperature? Temperature is a measurement of the average kinetic energy of the particles of a substance. So if you are increasing temperature, you are basically increasing the average kinetic energy of the particles. Now, how does temperature affect the rate of reaction? We are saying increasing temperature increases the number of effective collisions per unit time, thereby increasing the rate of reaction. Now, how does it do so? Increasing temperature increases the number of particles with sufficient energy for effective collisions, as shown in the Maxwell-Boltzmann distribution curve below. So this Maxwell-Boltzmann distribution curve, what does it show? On the vertical axis, it shows us the number of particles. On the horizontal axis, it shows you the energy, the amount of energy. Now, I need you to pay attention to this value on the horizontal axis, EA. What is EA? It is the activation energy. Now, that is the minimum amount of energy required for effective collisions. What you can see is we are having two graphs here. One is the one that is drawn at a certain temperature T1, and the other one is drawn at a certain temperature T2, which is higher, which is greater than T1. What is the effect? We can all see that at a higher temperature T2, the graph is shifted to the right, with the consequence that the number of particles with sufficient energy for effective collisions is increased from N1 to N2. At temperature T1, what is the number of particles with sufficient energy for effective collisions? You go to EA here, and then you extrapolate to the graph of T1. Once you reach there, you then go on to read off the number on the y-axis here, and then that gives you the number of particles with the minimum amount of energy for effective collisions. In other words, the area that is shaded in green here is representing the proportion of particles that are capable of effective collisions. Now, at temperature T2, what happened? We can all see that when you extrapolate, you reach that point, and then when you read off the corresponding value here on the y-axis, you are going to get a certain value N2 that is greater than N1. In other words, the number of particles with sufficient energy for effective collisions increases when you increase temperature, and therefore the rate of reaction increases. So it's very important to mention that the particles that are colliding effectively per unit time increases, because we are supposed to explain the effect of temperature according to the collision theory, right? Catalyst, and see how it affects the rate of reaction. There we are. So before we look at how the catalysts affect the rate of reaction, let us just quickly define what is a catalyst. A catalyst is a substance that changes the rate of reaction without being chemically changed. For example, manganese dioxide in the decomposition of hydrogen peroxide to form oxygen, O2 gas, and water, H2O liquid. Now, I gave a balanced equation for that reaction. So we are having 2 H2O liquid to give us 2 H2O liquid plus O2 gas. Now, you realize that I wrote my manganese dioxide above the arrow there to show that it is a catalyst, and I do not need to balance it in my chemical equation. So very important to realize that. Now, how do we show this on our Maxwell-Boltzmann distribution curve? The effect of a catalyst, if you come down here, you are going to see that on the vertical axis, we are having the number of particles, and on the horizontal axis, we are having the energy. Now, what I want you to see is, without a catalyst, you are going to realize that your activation energy, EA, the proportion of particles with sufficient energy for effective collisions, is being represented by the area shaded in red. But when we lower the activation energy to E-A after adding a catalyst, you realize that the proportion of particles that are capable of effective collisions increases, because we are now going to add that green area as well. So that is how you show on the Maxwell-Boltzmann distribution curve. You are just going to show on the horizontal axis that your activation energy decreases from EA to E-A there. And at E-A, it results in a higher number of particles that are capable of colliding effectively. You can use this graph of temperature T2. You realize that if you extrapolate from E-A, you are going to get a higher value of particles that are capable of effective collisions than at EA. Okay, now let's look at the effect of adding a catalyst to the rate of reaction. Let's start by defining what is a catalyst. A catalyst is a substance that changes the rate of reaction without being chemically changed, e.g. manganese dioxide in the decomposition of hydrogen peroxide H2O2 to form oxygen gas, O2 gas, and water H2O liquid. Now I gave a balanced chemical equation for the reaction there. So we are having 2H2O liquid to give us 2H2O liquid plus O2 gas. Now I wrote my MnO2, the manganese dioxide, at the above the arrow there because it is a catalyst, right? Now let's look at the effect of adding a catalyst to a chemical reaction graphically. Let's start by looking at the Maxwell-Boltzmann distribution curve below there. If we consider a certain chemical reaction that is having a certain activation energy, EA, the number of particles that are effective for collision will be increased if you lower the value of EA to E-A. Now you can see that when the activation energy is EA, the proportion of particles with the minimum amount of energy for effective collisions is represented by the red region there. But after we have lowered the activation energy to E-A, we can all see that the area increases by the green area there. So now the proportion of particles with energy sufficient for effective collisions includes the red shaded area plus the green shaded area. In other words, lowering the activation energy results in a higher number of particles that are capable of colliding effectively. If you consider, say for example, this graph, the graph at temperature T2, you are going to realize that at the activation energy EA, you extrapolate to the graph, then if you read off the number here, you are going to get N3. Now, after lowering the activation energy, you come to E-A, then you extrapolate until you reach the graph of T2, then you go on to read off the number that you get on the y-axis, which is the number of particles. We can all see that after lowering the activation energy, we are getting a higher number of particles that are capable of colliding effectively. Now, you may also be asked in the examination to interpret this Maxwell-Boltzmann distribution curve, or you may be asked to show graphically the effect of adding a catalyst. So you must just show that the line of the activation energy, it shifts to the left, with the consequence that you'll be having a higher number of particles with sufficient energy for effective collisions. Now let's look at this the progress of reaction versus energy graph. On the vertical axis we are having energy, and then on the horizontal axis we are having time. Now here we are having our reactants, and here we are having our products, and at the top, the summit of this curve, we are having what we call the activated complex. What is happening? You start with reactants that are having a certain amount of energy that you read off on the y-axis there. Then you supply energy in order to break the bonds in the reactants and then form an activated complex of free radicals. So you are adding energy, and that energy is referred to as activation energy. So you can see from here to there, that is the activation energy before adding a catalyst, and I depicted it by EA. Now, after adding a catalyst, what happens? Now we drew another curve which is having a lower height, E-A, which is starting from down there to somewhere below there. And you can see that the activation energy is lower with a catalyst. Now these two graphs are showing an endothermic reaction on the left here and an exothermic reaction on the right. How do you see that? You see it by means of delta H. What is delta H? We refer to it as the change in enthalpy or heat of reaction. It is the energy of products minus energy of reactants. Now, in the case of endothermic reaction, you are ending up with products that are having more energy than the reactants. So when you say E products minus E reactants, you are going to get delta H being greater than 0. So in the case of an endothermic reaction, the heat of reaction delta H is greater than 0. Now in the case of exothermic reaction, you can see we are starting with reactants with a certain amount of energy there. Then we end up with products that are having a certain amount of energy down there. So the products are having less energy than the reactants, such that when you substitute in this equation of delta H, you are going to get your delta H being less than 0. So if delta H is less than 0, it means it's what? Exothermic. If delta H is greater than 0, it means it is an endothermic reaction. And similarly, in the exothermic reaction, you may be required to show graphically the effect of adding a catalyst. So you can see without a catalyst, I'm having the activation energy, which I calculate from the difference between the energy of the reactants and the energy of the activated complex. Now, after adding a catalyst, we are going to end here. Then you show by means of a dotted line that the activation energy is now E-A, which is lower than EA, your initial activation energy, before adding a catalyst. Right? Let us proceed further and look at the effect of surface area on the rate of reaction. We say, according to the collision theory, increasing surface area increases the number of effective collisions per unit time, thereby increasing the rate of reaction. For example, powdered calcium carbonate CaCO3 solid will react quicker and the reaction with HCl, hydrochloric acid arc, reaches completion quicker than lumps of calcium carbonate solid, right? So I gave a balanced equation for the chemical reaction between calcium carbonate and hydrochloric acid. You know from your previous grades that a carbonate plus an acid, it gives you a salt plus water plus carbon dioxide. So the balanced equation will be CaCO3 plus 2HCl to give us CaCl2 arc plus H2O liquid plus CO2 gas. Now, how do we measure the rate of this reaction? We can measure the amount of carbon dioxide produced, or the volume of carbon dioxide produced with time, and that will give us an indication of the rate of reaction, as is shown by this graph on the left. You can see on the vertical axis I'm having volume of carbon dioxide in cubic centimeters. On the horizontal axis I'm having time in seconds. Now, if we were to plot the graph of the volume of carbon dioxide produced versus time, we are going to realize that we are going to get a curve as is shown there. Let's consider the curve with the lamp, which is the solid one, this one. You can see that as time goes on, the amount of carbon dioxide produced increases until it starts to remain constant at time t1. Right, what happens at time t1? Your graph flattens, it becomes horizontal. And what does it show you? It shows you that the reaction is complete. The reaction has reached completion. This reaction of calcium chloride and hydrochloric acid does not go on ad infinitum or forever. It stops. When does it stop? It stops when the limiting reagent has been used up. If it is calcium carbonate or hydrochloric acid that is the limiting reagent, once it gets used up, then the reaction reaches completion, right? So let's analyze the shape of this graph before we compare it to the one for the powdered calcium carbonate. We can all see that the gradient of the graph of volume versus time, it decreases until it reaches 0 at the time t1. Now, what does the gradient of this curve represent? The gradient is going to be change in amount, which is the change in volume over change in time, right? And what is the change in volume over change in time? That is your rate of reaction altogether. So I want you to know that the gradient of this graph represents the rate of reaction. So what is actually happening there? The rate of reaction is decreasing exponentially until it reaches 0 at time t1. But when you compare the graph when you are using a lump of calcium carbonate with that one where we are using powdered calcium carbonate, which is having a higher surface area, what do we see? We notice two things. One, the time taken for the graph to become horizontal is less. We are now having a time t which is less than time t1. In other words, when you are using powdered calcium carbonate, the time taken to reach completion for the reaction is less. And secondly, we can all see that the dotted graph is steeper, meaning to say it's having a higher gradient. And what did we say the gradient represents? It represents the rate of reaction. So that is what we notice in these two graphs. So they may ask you to sketch in the examination the graph that you obtain after using either a reagent with lower or higher surface area. It must show that it's having a steeper gradient, and then also it must show that it flattens out at an earlier time. So what that confirms is when you increase your surface area, then the rate of reaction increases. Now, looking at the graph on your right hand side, we said we can also measure the rate of reaction by checking the amounts of reactants that are used up with time. Now, if we allow the carbon dioxide to escape from our reaction up here, then obviously we expect the total mass of the reactant mixture to decrease with time in such a way that if we plot the graph of mass versus time, your mass on the vertical axis and time on the horizontal axis, you realize that if we start with a certain mass here, that mass is going to exponentially decrease until a certain time t1, where it flattens out and become horizontal, and at that time we said the reaction is what? It would have reached completion. Now, the solid line is showing when we are using a lump of calcium carbonate, and then the dotted red line is showing when we are using powdered calcium carbonate. It's the same thing. This time around, your gradient of this will be change in mass over change in time. Now, the gradient of the dotted line, you can all see that it is steeper and it also reaches or flattens out. The reaction reaches completion much quicker at a certain time t, which is less than the time t1 that we get when we are using a lamp. So very important to be in a position to demonstrate and analyze graphs that have to do with the effect of increasing surface area on the rate of reaction. Now let's proceed further to look at the effect of concentration and then pressure. Now with concentration, you need to remember what concentration, C is equals to N over V, and is measured in moles per cubic centimeter. So when we are talking about concentration, we are basically referring to solutions, right? How does increasing concentration affect the rate of reaction? We say down there, according to the collision theory, increasing concentration increases the number of reactant particles, which results in an increase in the frequency of effective collisions. Now, pressure is for gaseous systems. Increasing pressure, you are basically increasing the number of reactant particles per unit volume, which results in the increase in the frequency of effective collisions, thereby increasing the rate of reaction. Now, very, very important, if we were to plot the graph of concentration versus time, then obviously your change in concentration versus change in time will give you an indication of the rate of reaction, right? So this is what we did. Just to simplify it, go through this tutorial and then answer the past exam question that I sent you. Some of you are just quiet. I don't know, is it because you did not understand what we're talking about in the tutorial? So I have simplified it for you in this video. If you have got any questions,